Okay, so I was asked to speak about secondary anisotropy, what Cheng-Pei called 3 lectures about nothing. So that should probably be the Seinfeld lectures and not the Cabo lectures. I'm going to talk about reionization mostly today, and the second lecture on B modes and gravitational lensing, sort of pairing them together and looking at the secondary sources that are in the polarization field. And then the final lecture will be on cosmic acceleration. And hopefully this will point you, this is meant to be pedagogical and sort of a little bit scattered, and point you to the literature, some recent reviews. Of course, I'm going to be relying a lot on my own recent review with Scott Dodelson. But there, it's not on. Sorry, I hope you'll bear with me. My voice is going too. So anyway, point you to the recent reviews on the field and warn you that these lectures, unlike our event here, is not all-inclusive. and so I hope you'll go to these reviews to look at the literature, and I hope these lectures will help you do that. Okay, so what are secondary anisotropies in the CMB? So Cheng-Pei nicely described the linear theory that gives you the primary anisotropies coming from recombination, that is the event where hydrogen forms and the photons are mainly doing nothing after that, but a lot of interesting nothing. So most of the photons just stream right to you, and you see what you have on the last scattering surface. But there are a few interesting effects that tell us about the more advanced stages of structure formation in the universe. And I'll be going through, sort of in a timeline fashion, what happens in these 3 lectures. So I'll start with the earliest thing that happens to a CMB photon after recombination. That is, it can be rescattered during a period of reionization from early stars in the universe, the first things that come out of structure formation. And they have interesting imprints in the microwave background, which can do interesting things for other pieces of cosmological science. Like suppose you wanted to measure the growth rate of structure for dark energy. You would want to know what the initial amplitude of perturbations are to make a normalization of that. And as we'll see, that measurement is limited by how well we understand reionization. So even if you weren't an astrophysicist that were interested in early stars, you might be interested in it for other reasons. And I'll go through those. So the next things that can happen are the structure in the universe can lens a CMB photon. And that has interesting consequences also for gravitational waves. We want to measure polarization from gravitational waves, but the microwave background image in the polarization field is being distorted by these secondary effects. So can we understand the secondary effects well enough to get that kind of science out? And then what kind of interesting science can we get from the lensing of the microwave background itself? And finally, there are things in the local universe below redshift 1 that are imprints of the cosmic acceleration phase. And the 2 that I'll go through are the integrated Sachs-Wolf effect, which comes from the evolution of structure during the acceleration epoch, and the Sunyaev-Zeldovich effect, which allows you to look at rare objects like clusters of galaxies in the universe. All right, so here's a preview of the things that I want to explain. These are divided now, instead of in a timeline, into categories that are associated with scattering of CMB photons and from purely gravitational effects. So this is sort of the landscape. Is it on? Okay. Is this one on? Okay. This is the landscape of the power spectrum. Cheng-Pei told you that how these are calculated. These are the primary anisotropies, and these are the oscillations that you get in those higher moments that Cheng-Pei was talking about, transferred from the lower moments onto the higher moments by free streaming. And the effects that I want to talk about in the secondary anisotropy are first the main effect, which is a suppression of the anisotropy spectrum, and a regeneration from sources during the ionized phase below redshift of around 10. And then more towards the later parts of the talks this week, I'll talk about the gravitational effects. And starting with lensing of the microwave background, what lensing does to the spectrum, smooths the acoustic oscillations, generates power on small scales, and also generates interesting non-Gaussianity that allows you to do lens reconstruction. And the gravitational redshift effects from the photons traveling in and out of gravitational potential wells that are changing in time, both in the linear regime and in the nonlinear regime. Okay, so let's get started. Reionization. So here's the timeline. Changpei told you a lot about this epoch, recombination. And the photons mainly stream toward you as the observer out here. And you see mostly the recombination surface, but 10% of the photons are rescattered in the epoch of reionization, which is redshift 10 and below-ish. All right, so here's another version of that diagram. I'll be showing pictures like this a lot, so let me go through it. Out here is, well, you're here in the center as the observer. And out here is the surface of recombination. Most of the photons would just come right toward you, so you would see the fluctuations in the temperature field and the gravitational potential field on the recombination surface. But what happens if the universe gets reionized? So that's what I'm showing as the transition between black and white here. Well, Thompson scattering is then again effective. You have free electrons, and the rescattering of photons changes their direction. So you lose photons out of the line of sight from, say, looking in this direction and seeing a cold spot, and looking in this direction and seeing a hot spot. That photon goes away. Of course, photons are conserved, right? So there's statistically, for every photon that you lose, a photon comes in, rescatters into the line of sight, and it doesn't change, the overall spectrum of the microwave background. But what it does change is the anisotropy of the microwave background. Because if you look at this diagram, you look at the primary anisotropy, and now you're seeing parts of this plane wave fluctuation in the interior of the recombination surface. And here is it represented as the last scattering surface as viewed from the electron during reionization here. But all of these temperature fluctuations that were the primary fluctuations are randomized. That is, you're equally likely to have a photon come in here as in here. And when you average all the photons that are rescattered into the line of sight, you have a net suppression. And this is the familiar e to the minus tau suppression. Changpei described this all in terms of the Boltzmann language for the more astrophysically minded people here. That's the same thing as the radiative transfer equation. And all I'm describing here is the formal solution to radiative transfer. Now, of course, this is the primary anisotropy being suppressed. So you might wonder, what else happens, right? So in fact, there's sort of an interesting, if you were just coming at this from ab initio, you might wonder about this, right? There are sources of anisotropy and that are regenerating the anisotropy, just like the sources on the recombination surface. So why aren't secondary anisotropies much, much larger? Changpei described that the universe is in a much more advanced state of structure formation at low redshifts than it is at high redshifts. And you might wonder, why is it that if I'm scattering a fair fraction of photons, 10% of the photons, why is it that the anisotropy is still much smaller than the primary anisotropy, even though everything that was a source in Changpei's equation is much, much larger, right? Density fluctuations are going nonlinear, so at k is above 0.1, they're actually nonlinear, above 1, not 10 to the minus 5 like they are at recombination. The velocity field is 10 to the minus 3, not 10 to the minus 5. So even things that are very simple to calculate, like the Doppler effect, fraction of photons scattered, velocity field, that's the temperature anisotropy. You would get a dipole anisotropy of the scattering. And why isn't that 10 to the minus 4 instead of something that is much, much below the primary anisotropy, which is 10 to the minus 5? And that's because of this, this solution to the Boltzmann equation, this radiative transfer solution, or in terms of the astrophysical nomenclature, the Limber approximation. So let's take this apart and look at the sources from secondary contributions and generically how they contribute to the anisotropy, and why is it that suppression is the main effect. So here's a little formalism. So the people, this is essentially the first thing you learn in radiative processes or radiative transfer if you had a Rybicki-Lightman course. But if you wanted to look at the effect on the radiation field of having sources along line of sight, all you do is integrate all the sources up. The one complication for us is that the sources have spatial structure, right? These are these plane wave fluctuations. They're varying on space. And they also have angular dependence. Say you were doing a Doppler effect, you'd have a dipole angular dependence. Later on, when I talk about the polarization, it's a quadrupole source. So you have a local angular dependence of the source. You're integrating that up depending on how you're looking at the source. And it's also varying in space, but in a very simple way where you can look at one Fourier mode per Fourier mode in the linear theory. So mathematically, I just wanted to show you a little math behind this. What you're doing in this formal solution of radiative transfer, which I'll show you in the next slide, is you're decomposing those two pieces to get the source that's pointing at you in a given line of sight on this part of the sky. And that's plane wave decomposition in angle on the sky and the local source angular dependence of what's doing the emission. And you put those together, it's just, for the physics-minded, it's just a Clebsch-Gordon series. You're resumming angular momentum, and you get the total source and the formal solution to radiative transfer. So the hierarchy equations that Changpei showed you have a formal solution that's no more than the formal solution of radiative transfer. That is, you have sources, you integrate them along the line of sight. This is coming from the spatial dependence of the plane wave on this line of sight versus this line of sight, and that turns into mathematically a Bessel function here. And then you have this obscuration. If there's stuff in front of you that's scattering the photons, you're losing the source. You're not seeing the source behind it. Instead, you're seeing the sources in front of it contributing, and you integrate this all the way up along line of sight. That's the formal solution to radiative transfer. Why do I say formal? It's because if you looked at what the sources were all those density fields and velocity fields that are also coupled to the radiation. So you have to know the radiation field before you know the sources, and that's why it's a formal solution. And as Changpei described to you, what you really do is you have a limited set of the hierarchy equations and moments of velocity field. You truncate that, you solve for these low-order sources, and then you stuff that back into the formal solution of radiative transfer. That gives you the multiple moments of the temperature anisotropy, and you construct the power spectrum as the two-point function of that. Anyway, that's the formalism, and that's what things like CMB fast and CAMB do. But let's take a look at the implications for secondary sources and why they're different from primary sources. So here's the pictorial view of that. I have the last scattering surface. I have the sources. The sources that exist on the last scattering surface are on this thin shell that's just the thickness of the duration of recombination. The difference with secondary anisotropy is they're coming from this interior region, say below the redshift of ionization or during the acceleration epoch. They're all contributing widely along the line of sight. And that means that when I take this decomposition of the source to look at its contribution per line of sight, that's this Bessel function here, I'm integrating through many crests and troughs of this plane wave fluctuation, which is the same thing as saying that I'm integrating across this oscillating function, which is the decomposition of the plane wave on the sphere. And that's the content of the Limber approximation. That is, if I'm looking this way, I see very little source contribution because the sources from here cancel from the sources in here. And if you view a more extreme version with a much shorter wavelength fluctuation, you'll see that I really get no contribution here. The only place that I get contribution is if I'm looking right along the crest or trough of the plane wave. And that means that the contribution is very much suppressed from where it is intrinsically. So the source power spectrum being very, very large doesn't matter if once you integrate through all of the contributions along the line of sight, they all cancel. So that's the generic story for secondary anisotropy. Although the universe is in a much more developed state, all these sources are contributing along the line of sight all the way back to recombination, or at least all the way back to reionization, the reionization surface. And all of these contributions are suppressed just geometrically by cancellation. Okay, so now let's take a look at the result for the primary anisotropy. So let's see if this works. As advertised, what mainly happens is that the anisotropy gets suppressed. You'll note that the large angle stuff doesn't go away, and that's exactly for the reason that I told you in the last slide. That is, it's only the short wavelength fluctuation that suffers this cancellation. So for the very long wavelength modes, for everything that I'm losing along the line of sight by scattering out, I'm gaining the same thing back, and I get no suppression for the long wavelength fluctuations. So this looks like as if I were tilting the whole spectrum to the red, that is, suppressing the small scale anisotropy. These things we'll talk about in a few moments. These are the polarization field of the microwave background, and that's a much cleaner tracer of reionization, since polarization directly reflects the scattering events. All right, and this is the topic for the next lecture. This is what happens to the B-mode fluctuations. All right. So that plot showed you something interesting, right? That was sort of an impediment interesting. That is, what reionization does to the primary temperature anisotropy is it suppresses the short wavelength stuff, the small angle stuff, and not the large angle stuff. So that looks like a tilt. And there is a degeneracy between the intrinsic tilt of the spectrum, how non-Harrison-Zeldovich, how deviant from 1 is this scalar spectral index, NS, versus the optical depth. If you just had the temperature information from the first few acoustic peaks, and this was the status when WMAP 1 came out. And I'll tell you later on in this lecture how polarization helps that in isolating the ionization history. And also I want to point out that this is not a true degeneracy, right? This is not something that looks exactly like tilt, because all of the short wavelength fluctuations are suppressed by a constant factor, e to the minus tau, not a tilted thing that continues to suppress things at small angles. So in fact, for the Planck mission, this is not even a degeneracy at all. There is no tau NS degeneracy for Planck because it can go across the acoustic peak spectrum and get tilt out independently of the ionization. All right, so that's the main effect, and that's a suppression of the primary anisotropy. But what about those secondary sources? I told you they're small. How small are they, and what are they? So let's start with the simplest one, the Doppler effect. What does the Doppler effect look like? All right, so the Doppler effect is this. Remember, I told you that if you just did a naive analysis from just looking at order of magnitude stuff, you'd say, oh, 10 to the minus 3, 10 to the minus 1, that's a 10 to the minus 4 fluctuation. I should be way up here. The Doppler effect actually contributes way down here. And in fact, the linear one isn't even the dominant contribution unless you're on scales of degree and above. That is, nonlinear effects already come in, even though you're dealing with very small fluctuations because of this geometric cancellation. So why is it particularly bad for the Doppler effect? And this has to do with this angular dependence of the source. So in the first simplest diagram I gave you, well, you had all these sources, you're integrating them up along the line of sight, and then there's this limber cancellation if you're looking this way versus this way. But what happens when you have a Doppler effect? Well, a Doppler effect is from the line of sight velocity relative to us, right? So if you have a plane wave fluctuation, Changpei told you that you have no curl to this field, so the fluctuation in the velocity field is pointing in the same direction as the k mode of the fluctuation. That means that if you're looking along this direction, where you have your contributions not suppressed by geometry, what happens is you have no velocity field along the line of sight contributing in that direction, whereas in the limber suppressed direction is where you get the contributions, but is limber suppressed. So the net result is that you're in even more trouble with suppressing secondaries for the Doppler effect. That is, not only do you have the straight out cancellation of crests and troughs, you also have a penalty because of the angular dependence of the source function here. Okay? So in that math I showed you, all that is that I'm recoupling a dipole, an L equals 1, to the plane wave angular harmonic here. And that gets you L plus or minus 1 coupling, Clebsch-Gordon coefficients. And when you look at the recoupling of these radial functions, what that is the Bessel function's derivative, and that has no peak here, and you get no contribution, a very suppressed contribution. All right, just to firm up that statement, the picture is here. Well, you have very, very little linear Doppler effect, right? Because what happens is if you're looking at these small scale fluctuations, you have cancellations from the velocity field falling in and falling out. That's the limber part of it. And in the region where you don't have cancellation, that is for things that are going transverse to the line of sight, you have no Doppler contribution at all. So how do you escape this, and why are there extra effects that come in at nonlinear order? So these are the modulated Doppler effects. What do I mean by that? Well, suppose I had a large-scale velocity field. So now I get to have all of the free electrons moving in the same direction. But I just modulate the probability of scattering, either through changing the density field to have a density contrast, an overdensity, or an ionization fluctuation, say a bubble during reionization. What happens now is that I have a mode going transverse to the line of sight. I have a contribution that is going across the sky, and I have a velocity field that's pointed at me, right? And that's geometrically allowed. That's the thing that gives me a contribution from the Doppler effect. So what are the ways to do this? The density field, right? So linear density fluctuations can modulate this large-scale velocity field and generate small-scale anisotropy on the scale of the density and homogeneity. And this is called the Ostreicher-Vishniack effect. And the Ostreicher-Vishniack effect has a broad distribution in contribution in redshift from any point where the universe is ionized. This is an old version where it could be a 50, but this is a really old plot. And it shows up after the CMB primary anisotropy is damped away by diffusion damping. You see this secondary anisotropy pop up, and it tends to be on 10 arc-minute scales and below, few arc-minute scales and below. And I won't go through all the modern approaches to this. I encourage you to go to Shirley Ho's talk about how you might extract things like this out of cross-correlation techniques. So that's one contribution. The other contribution is if ionization is inhomogeneous, you have extra probability of scattering in an H2 region versus a neutral region. So you get a modulation in the same sense from the inhomogeneity in reionization. This is something that my student who's here, Michael Mortensen, worked out based on a semi-analytic technique from Oliver Zahn, who I think will be here later in the week. But anyway, here is a picture of what you might expect the ionization field to look like here. And that modulates, instead of a sharp transition between black and white here, you have a region where it's ionized in bubbles. And that can also modulate the Doppler effect. So to remind you, here's that large-scale velocity field. Here you get no line of sight contribution, but say in this region, I have all of the free electrons moving in the same direction in this idealization here, but I have enhanced probability of scattering in these ionized regions. So again, this reflects the scale of this inhomogeneity, this time not in the density field, but in the ionization field. It's called patchy or inhomogeneous reionization. It also tends to contribute at the sub-microkelvin level on scales that are beyond the damping tail. You see this extra contribution pop up here. And I also urge you to go to Kendrick's talk, which is about how you would try to extract this. I'll mention this again in terms of the polarization effect that's analogous, but how you might use this to get out the properties of the ionization history. All right, so those are the main temperature field effects. And those are a suppression of the temperature field and a generation of small-scale anisotropy. But how have we learned the most about reionization today from the CMB? That's through secondary polarization. So let me just go through the basics of polarization. This is the first detection, actually an anomalously high detection from a cross-correlation between temperature and polarization. It's now come down a little bit. Let me review for you the basics about why reionization polarizes the microwave background, or scattering polarizes the microwave background. So we're talking about Thompson scattering, the scattering of photons and free electrons. If you have radiation incoming, there's a polarization dependence of the Thompson differential cross-section. And all that means in a semi-classical sense is that you're accelerating the electron along the electric field direction. And that means if you're staring down this line of sight, only one of the polarization modes pass through because you have transversely polarized photons, not longitudinally polarized photons. So that has the ability to polarize the radiation field, but only in conditions where you have anisotropic radiation, right? Because if you looked at that thought example and said, well, the photon can come from this direction or this direction. It's not like the sun where we have a single source. We have a nearly isotropic source, right? So if you have a fully isotropic source, for every photon that comes in this way and gives you one polarization state, a photon comes in from the orthogonal direction and fills in the other polarization state, leaving you with statistically unpolarized radiation. Whoops. So how you really generate polarization is from having a quadrupole anisotropy in the temperature field, the intensity of radiation coming in from 90-degree angles. And this time you have a net linear polarization because the orthogonal polarization state has a different intensity given that its source at 90 degrees has a different temperature. And just to keep in mind, it's aligned with the cold lobe of the quadrupole anisotropy in the background. Okay, so why do we have quadrupoles? This is what Chung-Pei referred to as anisotropic stress for the microwave background. Anisotropic stress is a quadrupole moment. And it comes about by free streaming for the reionization pieces of polarization. It's easy to see, right? If you had released the photons from recombination and they were hotter here and colder here and hotter here, you would generate a quadrupole anisotropy to the electron sitting in the middle of here. and that electron would rescatter the radiation into something that has a linear polarization. And of course, we do have anisotropic radiation. That's the temperature field. It's just to remind you. And geometrically, it's easy to understand what kind of polarization field you get, right? So suppose the quadrupole moment were uniform across the sky. What is the polarization pattern you would get? Well, as we said in the previous slide, it's just the projection of the cold lobe of the quadrupole anisotropy. So now there was this sky diagram, and I'm going to go through from the equator to the pole and back to the equator to show you what the pattern of linear polarization should be for a uniform quadrupole anisotropy on the sky. So the projection of this quadrupole moment gives you the length of the polarization vector here, the headless vector. So it's maximal here, it goes through a 0 by symmetry, and goes back maximum. And that's just the geometric way of viewing what the fancy name for this is spin spherical harmonics. That's the spin spherical harmonic. It's easy to see from that diagram geometrically what that is. Let me give you the math. So polarization fields are this 2 by 2 traceless tensor, right? And mathematically, you want a complete set that describes the sphere. If it were just a number for each position on the sphere, you know what that is. That's the spherical harmonics. If it's a tensor field on the sky, the generalization to that is the tensor spherical harmonics, or the spin 2 spherical harmonics. They're again just the eigenfunctions of the Laplace operator on the sphere. It's a complete set. And this was just to show you that it's easy to understand the geometric content of what they look like on the sky. Okay? So again, it's just this recoupling of angular momentum. And this is the quadrupole moment, L equals 2, M equals 0, so-called E. I haven't told you what E and B are, but this is the polarization pattern from that density field fluctuation that you would get on the sky. And the final piece is, there were 2 pieces. Remember, to do the radiative transfer solution, I need to know the angular structure. I also need to know the spatial structure. Spatial structure is still a plane wave. The quadrupole moment can be modulated by this plane wave. So I go through crests and troughs and crests and troughs, where the quadrupole moment sign flips as you go from one to another. And that is just depicted here as this modulation of the amplitude, or reversing of the sign of the polarization if we're going across the from a crest to a trough. But anyway, this is again just a recoupling of angular moments. And the interesting thing for us here is that instead of this broadly oscillating function you got for the temperature field, is a really peaky function. So geometrically, it's because if I'm looking at the equator, I get most of the fluctuations. At the pole, nothing. And that localizes the angular dependence of the contribution of the plane wave very nicely. And that makes things like detecting features, say you want to detect features in the inflaton spectrum from looking at the microwave background. Polarization is great because polarization gives you a really, really sharp transfer function. That is, if it's sharp in K space, it's sharp in L space as well. And I'll give you an example at the end about that. So those are all the good things about polarization. It's due to scattering alone, so it isolates scattering effects. It has this directional dependence, which both localizes an angle fluctuation in space, and also we'll see has 2 pieces of information, because it's not just one number per position on the sky, it's a tensor, where it has a directional dependence, and that's what the content of this E and B mode stuff is. So of course there's got to be bad news, right? The bad news is that it is the same as the good news. It's generated by scattering. So it's only in conditions where you have some optical depth that you get enough scattering to get polarization. But if you had very, very high optical depth, what happens? If you had high optical depth, then the directions of all the photons are going to be randomized. It's in this so-called tight coupling regime that Changpei talked about. And in that case, you don't get quadrupole anisotropy. If you're the electron sitting here and the photon has changed its direction many times and going from a hot region to a cold region, you don't have any anisotropic radiation. And that again suppresses the source of polarization. So polarization is generically much smaller than the temperature for fundamental reasons. It's generated by scattering alone, and it's suppressed by scattering. So that means only in the intermediate regime of finite optical depth, small optical depth, like a 10% optical depth situation, would you get significant polarization. So what's the good news? Well, the good news is reionization is a situation like that. It's optically thin, and that's where you expect to see polarization at about a level of a factor of 10 down from the temperature field. All right, so here is the WMAP3 data, and now the best constraints are coming from the autocorrelation, the power spectrum of the polarization field itself. The first detections were from the cross-correlation with the temperature field. And let me just complete the picture by reminding you how to put this all together. All right, so back to these circle diagrams. Here is a long wavelength spatial fluctuation going across our whole horizon volume here, with recombination sitting at the outskirts here. The primary anisotropies are looking at this little slice of it from recombination. Most of the photons just go right to you. About 10% of the photons are scattered during reionization. And those ones that are scattered see this last scattering surface sharing the plane wave structure of the gravitational potential, the Sachs-Wolf effect that you see in the primary anisotropy, shared here. And then as you go across the sky, you see different sections of this plane wave, just like that diagram I showed you of looking at the quadrupole moment ascending across the sky. And that's also why they're correlated. They're sharing the same Gaussian fluctuation from this long wavelength fluctuation here. The Sachs-Wolf effect that you see in the temperature field is correlated with the large angle polarization, in this case, the quadrupole moment of the polarization field that you see on the sky. And that gives you a cross correlation between the two. That was what was first detected, and that's what gave the high value of the optical depth. But it was also consistent with lower values that are now the state of the art. In terms of the optical depth, it's something like about 9% of the photons rescattered during reionization. All right, so why do we care? Well, that 9% is still kind of high, right, compared to the quasars. So it might imply an extended period of ionization and puzzles for how the first generation of stars might do that, maybe even indicating more exotic physics is involved than just ordinary star formation. So that's the astrophysics reason for, one of the astrophysics reasons for studying it. There are other reasons that you might be interested in reionization. Reionization, as we talked about it in the first part of the talk, screens the temperature field. And on small scales, so the normalization that we get from WMAP is mainly now small scale fluctuations, small from the microwave background standpoint, Ks of 0.05-ish. And that is something you might want to compare if you're interested in dark matter and dark energy, right? Because as Changpei told you, given a dark matter and dark energy theory, we can predict what the growth of structure is. We know what the amplitude of fluctuations are at redshift of 1,000, where the CMB recombined, if we knew what the scattering screen in front of us is from reionization. So how well you can measure the growth rate of structure from comparing the local universe to the ultra-high redshift universe depends on how well you understand this reionization netbook. So to put physical content in it, if you're interested in neutrino masses, or you're interested in the dark energy, cosmic acceleration, it becomes important to know what reionization is doing. It also offers another window on the basic physics in two ways. It's another way of probing the large angle sky. So there are odd things going on in the microwave background temperature that are sort of hovering at statistical significance. If you believe any of them are significant, you would see it, the polarization track that. And I'll give you two examples of how that might work. But the main thing is that it gives you another handle on the largest fluctuations in the universe. And it also presents, as well, a second window for looking at gravitational waves that I'll talk about in the second lecture. And this is advertisement for my student, this poster, Michael Mortensen. So please go talk to him about this. This is just to reiterate that point that I made, that reionization is important because in other regards, we can already predict the growth of structure from distance measurements. These are the current measurements, the union plus WMAP5. And so if you were trying to falsify a cosmological constant, and you can do this more generally, but this is a cosmological constant, measuring things about the growth of structure, as we'll hear later in the week from things like lensing and the cluster abundance, is a great way to falsify the standard ideas for dark energy. That is, we already predict what we should see to better than 1% from even current distant measurements, and we haven't measured it yet to that precision. So it could falsify a cosmological constant. So Michael Mortensen has a poster about that. All right, back to reionization. How am I doing in time? 10 minutes? All right, so what's the challenge here? Well, the challenge is we've got this measurement of an E-mode power spectrum, and what's important for the small scales is the total optical depth. But what if you didn't know how reionization proceeds, which is, reionization is a very complicated process. If we didn't know how it proceeds, can we really translate what we see on the sky in the microwave background polarization to the total optical depth for that measurement of the growth history, for example? So here's just an example of different ionization histories. This is a really toy, simple model to just show you what could happen. So suppose I had the same sort of optical depth, the same total number of photons being rescattered, but in one case, only at low redshifts. This is matched to WMAP1, so it's a pretty high redshift for this example. But anyway, let's go to a higher redshift, but a lower level of ionization covering the same optical depth, the same amount of scattering because you had scattering at high redshift to compensate the lack of scattering at low redshifts. What do you see in the E-modes? Well, you see a different E-mode pattern, basically a geometric thing again that you see the project. So these things are generated by quadrupole moments. Quadrupole moments are fluctuations that are on the horizon scale at that time. So it's basically just the change in the horizon size as projected on the sky that tells you where they're contributing. So higher redshift means it's contributing on a smaller angle, smaller scale, higher L. And that changes the shape of the E-mode power spectrum for the same optical depth. So suppose you went about analyzing it with the wrong ionization history, what would happen? You would bias things, right? You would say that, okay, I take WMAP and I take instantaneous reionization, which is the usual approach. And you would infer from that a tau and infer from that in your big MC-MC chain the implications for, say, dark energy or cosmic acceleration. And you might think you falsify a cosmological constant where you really haven't. So let's take a look at this in more detail. So in terms of contributions in redshift, you can look at contributions from discrete intervals in redshift, see what they do to the CMB E-mode spectrum. So the lowest redshifts contribute the large angle stuff, and I'll show you that's kind of interesting also because we know that the universe is ionized below 6-ish, right? And that means that the large angle stuff is extremely well determined from the model side. There's no way that ionization can produce interesting differences at the quadrupole of the the CMB polarization. And that means that if you measure something different, you've said something very dramatic about the underlying model, that it's not a smooth power spectrum, say, or it has some consequence like the temperature field anomalies, that it looks different from anything that is possible in an ionization history sense. So that's one thing. And then at higher redshifts, you generate these interesting bumps and wiggles at the regime of L of 20 to 30 that are potentially measurable by Planck and CMB pole. So as we go into the epoch beyond WMAP, I think it'll be important to do a more careful analysis of this. And this is, again, advertising my student's work, Michael Mortensen. So it's not a fundamental limitation. You can do better than just assuming the wrong ionization history and getting a biased result. And the nice thing is that you can get a complete set of functions that describe all of the observable properties of the ionization field on the large angle polarization field in the microwave background and do a complete statistical analysis. This, for the experts, is a principal components approach that just rank orders modes. You see in this figure, the problem is that neighboring redshift bins give very similar effects. So I can't extract redshift 25 versus 24. They give very correlated effects. So what you can do is look at the average in a certain weight, which is a principal component weight, and that's very well determined in the low order moments. So this is a principal components decomposition. This just says that only the first few principal components are important. That is all that you will ever need to interpret the microwave background E-mode polarization is 5 moments, so that's easy. You throw that into Cosmo-MC or your MC-MC likelihood chain and do the full analysis. This is just showing you that that's true as you look at model by model. And this is work from Michael Mortensen looking at WMAP5 data. So WMAP5 doesn't have very much information beyond tau, but as we go to Planck, this will become important to do. And it does also say that WMAP5, the information that you have in WMAP5, has interesting properties that if you wanted to complement what we already know, you want to measure things in this regime, L of 20 to 30, because the high redshift ionization history, which is beyond the abilities of things like 21 centimeter to probe, those still aren't determined by the microwave background yet. And measurements here will complement what we know about ionization in that sense. The low redshift, the large angle stuff is actually quite well predicted. That is, independent of anything that can go on at high redshift in the ionization history, we already predict what the quadrupole will be better than we can measure it. This is the cosmic variance limit on how well you can measure the quadrupole. That means that if you measure it and get rid of all the foregrounds, and it turns out to be high or low, then you have an interesting violation of Lambda-Cdm in some form, statistical isotropy maybe, or features in the power spectrum maybe. But anyway, you have a handle that cannot be explained by ionization history. Okay, and this is the last bit, which is just some examples of that. So these sorts of anomalies that I've been alluding to have been really popular to look at in literature. Unfortunately, they're all a posteriori. So you're looking at a cherry-picked statistic and thinking, oh, well, that would never happen, but that's because you post-selected it. That's because your eye looks for anomalies and you're not taking into account how many you did. So are they significant or not? That's a debate in the literature. Some interesting things are the quadrupole and octupole are aligned, and they're also curiously aligned with the ecliptic to give different power in the two ecliptic hemispheres. So if any of this has a cosmological explanation, you would see the same sort of thing in polarization, right? So when we can measure the quadrupole and octupole in polarization, which is not yet because of the galaxy, what you should see is if it had, if it were completely Gaussian random, nothing to do with the temperature field, say from a completely different effect, and things like the anomalous quadrupole being low and the quadrupole octupole were a foreground effect, you would see no alignment in the polarization field, something like this, random. If they were generated cosmologically through our standard Lambda-Cdm model, we would see a weak alignment just because temperature and polarization are correlated by the Sachs-Wolf effect. And we have things from the dark energy side that make them decorrelated. That's the ISW effect. And if they had a really bizarre physical explanation, like some of these long wavelength multi-field inflation explanations where you have this modulation of the spatial field, you would actually get a strong alignment of polarization. Similarly, for things like features in the temperature power spectrum, there's been speculation that maybe these aren't just statistical flukes, these features, and maybe they have a more fundamental origin in inflation. So suppose they did, well, you would produce features in the polarization field, And of course, you have to be careful because as we were looking at the reionization effects, you can get features from reionization. So again, this is advertising Michael Mortensen's work. If you try your best to make a mimic model, that is, try to enhance and reduce features in the right way to make a wiggly power spectrum from inflation look like a smooth power spectrum, it still will turn out to be statistically significant. It's hard to mask features in the polarization field unless you have really bizarre things going on at very high redshift in reionization. All right, so here's the summary of the first lecture. The main effect from the standpoint of what happens to the primary anisotropy is that small angle, large L anisotropy is suppressed, and just from the formal solution of radiative transfer, you see this as losing photons that have the anisotropic pattern out of the line of sight and regaining photons that are averaged across temperature fluctuations, replacing them. You get sources, that is, they're replacing them, but not just with primary anisotropy, but with secondary anisotropy, but because they're contributing all across the line of sight, contributions from crests or overdensities and contributions from underdensities cancel along the line of sight. That's called the Limber approximation. And the Limber approximation is the mathematical thing that's suppressing all of these contributions, even though structure formation is at a much more advanced state. The net result for the temperature field is it looks like a tilt to W map, which can only see the first 2 to 3 acoustic peaks. It's not a limitation for Planck, which can see beyond that. There is no tau tilt degeneracy in Planck. And also, there's no tau tilt degeneracy if you have polarization giving you an accurate measurement of tau. And I went through how accurate is that measurement of tau. I probably skipped through the bottom line for that. The limitation from principal components that you derive is something like 1%. So if you are generous and allow the ionization field to do anything you want from redshift 6 to 30, you should still be able, in principle, to measure the optical depth to 1% and complement things like measuring the growth of structure from measurements today at 1% level. Okay, and that's this stuff that the polarization spectrum carries sufficient information to get tau independently of the ionization history. And it also has some handle on whether there's really high redshift ionization or whether all of it's coming from low redshifts, which is interesting from the structure formation standpoint. And finally, it gives you another window, and the example today is that it's another window on the largest angle fluctuations in the universe. They're cosmic variance limited in the temperature field already. We will not know anything more about it statistically, although we might have better foreground models, for example, from the temperature field. But they give you another opportunity to explore what's going on and for horizon scale wavelength and things close to the horizon scale. And I gave you 2 examples of that. Thanks.
Current status about non-Gaussianity constraints, and in your opinion, what is the main way to constrain this initial cosmological factor?
Mm-hmm. Is Kendrick here, or did he skip out? You should get Kendrick Smith to give you the update on that. Yes, there have been claims that FNL, the quantity that you measure from the microwave background and from large-scale structure. But in the microwave background, WMAP3, Ben Wendahl and company showed depending on how you view several sigma, a marginal detection of FNL. They came down a little bit with WMAP5 into a less significant, but still there effect. And Kendrick, I don't think it's published yet, but has an upper limit that I think is something like 50 or something. Kendrick here. FNL less than about 50 at 2 sigma. Now, there's a complementary way of looking at it from large-scale structure. That is, if you look at bias tracers of large-scale structure, you see a scale dependence. You see not linear bias, but you see a feature that has a change in the bias at very long wavelengths. And that also gives comparable constraints, but no detection.
You should say that FNL less than 100 means less than 10 to the minus 4.
Yeah. That's also very impressive from the microwave background standpoint in that we're looking there for a really tiny second-order effect. The fluctuations are 10 to the minus 5, and units of FNL is in that unit. So a FNL of 1 is a 10 to the minus 5 on that, a 10 to the minus 10 type fluctuation. So it's quite impressive that they're at that level in the data. And that also makes large-scale structure appealing because it's actually an order unity effect in the large-scale structure side if you can get to long wavelengths.
The power asymmetry is also with the non-Gaussian effect. It just doesn't show up in an FNL analysis. So
that's right. So
which way you look for it.
Right, and it depends on what you call non-Gaussian. So you can explain those things with things that are violations of homogeneity, isotropy, and Gaussianity, but not necessarily Gaussianity. So it's really homogeneity. It's really isotropy that you need to break to do that.
Any other questions? Well, before we go to the coffee break, there is an announcement. But before the announcement, let's thank again Wayne.
I will be receiving the contributed talks of today during the coffee break, so you can just go just here and give your talks, especially the talks of today. Okay.